Welcome back. Last video we have seen the rigorous proof of Fourier integral theorem. So, like that, given a function f(x), if you start with and do the Fourier series, write its Fourier series and you fix some x values, you will see that you end up getting some number series, and you will that number series the value of the number series, sum of the series is known. The same way, in the Fourier integral formula you can substitute some non-periodic signal, that is piecewise continuous and absolutely integrable function f(x). Left hand side is f(x), and the right hand side you have a double integral, and if you can evaluate one part of the integral, and what remains is the other integral. So, you will see that some integrals values analytically from this formula, okay, that we will do later. That is one application of this Fourier integral formula. So, once you have this Fourier integral formula, so now you can define what is a Fourier transform and its inverse transform. So, that is legitimized, whatever we have defined as Fourier transform and its inverse transform, and you have certain properties that we have proved. Based on these properties, you make use of all these properties, and we try to solve some problems. First thing is, what do you mean by problem? Problem is we try to apply this Fourier transform to solve certain problems in physics and engineering. So, for example, problems means either they are ordinary differential equations with initial conditions, or ordinary differential equation over a domain with boundary conditions. So, something like that, if you have some ordinary differential equation, linear ordinary differential equations, you can easily solve by applying Fourier transform. And the same way, if you have some PDEs, partial differential equations. So, partial differential equations, if you have seen in differential equations course, any linear partial differential equations in two variables, so that is that you can classify into three type of typical equations. So, typical of such equations are for elliptic type we have a Laplace equation, and for parabolic type it is a heat equation, and for hyperbolic type equations you have wave equation. So, you have typically three equations which are wave equation, heat equation, and Laplace equation. That is, you can also think of two dimensional version of parabolic heat equation, that is a steady state of a heated plate. Okay. So, if you think of like that, so you will get a two dimensional Laplace equation. So, these are the three typical equations which you can think of as from any second in two variables, second order partial differential equation in two variables. Then we can solve such problems over certain domains. That is what we have seen in the differential equations course. If you have seen earlier, if you have done differential equations for engineers, you have seen how to solve such partial differential equations in certain domains. So, those similar such problems, these linear equations, these are actually linear equations, all three types. These equations with some boundary conditions or initial conditions, you can actually solve by using the transform techniques, either Fourier transform, and later on you can apply Laplace transform and other transforms which you can use. Okay. So, you have to suitably use these transforms and try to solve these boundary value problems. So, that is one such application. So, you can solve ordinary differential equations with the initial conditions, partial differential equations with initial and boundary conditions, and this is one application. And you can also based on the properties of the Fourier transform, you can evaluate some integrals. Other type of equations that you can solve, other application of partial Fourier transform is solving integral equations. So, integral equation is you have something like same like it is analogous to the differential equation. In the differential equation, what we mean is an unknown in the derivative. So, in the same way, if you think of if your unknown is in the integral under integral, that is called the integral equation. So, if you can solve certain type of integral equation, I will give you a certain form of such linear integral equations you can solve by Fourier transform. So, that is another application of this Fourier transform. So, we will see one by one. So, let us see the applications of application of Fourier transform. Fourier transform, now we mean many. So, what we mean is Fourier transform. So, either Fourier coefficient, that is Fourier transform as in a complex form over a finite interval, or you can think of if it is a even function or odd function, depending on that you have either sine transform or cosine transform. You call this Cn, n even, you call this cosine transform, or rather if you are working with Cn's are a complex Fourier transform of a finite signal. And if you have Fourier series in terms of an and bn, and an's if an's are 0, bn's are nothing but Fourier sine transform, and an's are Fourier cosine transform, if just for the namesake. So, those are over for transforms over a finite intervals. Okay. So, later on what we have is a Fourier transform over a full real line, that is in terms of exponential function, integral minus infinity infinity f x into exponential function. And also we have defined in a different way. So, if your function is defined only on from 0 to infinity on semi infinite intervals, if you have a cosine transform and sine transform and its inverse transform. So, depending on what is your domain, we will try to apply one of these transforms. Ordinary differential equation, first application is to solve ordinary differential equations. Equations that are linear, linear of any order. So, let us choose Ly. So, let me call this L, y is an unknown, this is depending on only one variable, one independent variable x. So, that is what is called ordinary differential equation. This is you have some constant a n, so, and you have nth derivative of y, and you have a n minus 1, n minus 1th derivative of y, and so on. You end up getting a1 dy by dx plus a naught of y equal to, if you have some forcing. So, in the system, so normally you get the right hand side f x, this is called a forcing term. That means in applications, basically if you have some force, outside force, this is the governing equation we will have on the right hand side, that is a non-homogeneous term. So, you have this such equation is, if you get a equation like this, this is a linear ordinary differential equation of order n. Okay. So, such equations how do we solve? So, if first of all to see this equation immediately, what is your domain? Domain is from minus infinity to infinity. So, that is what it means. If nothing is given, means a domain is minus infinity to infinity. So, how do I solve this? By using Fourier transform. So, you will have a Fourier transform over full real line. So, if you apply y cap, you apply Fourier transform, For example, if your domain is 0, then I apply Fourier cosine transform or sine transform. Okay. And once you have this domain, the boundary is this, x equal to 0 is the boundary. On that you should have the information, that is n initial conditions, n boundary conditions you should have. Okay. So, at x equal to 0, this is the initial value problem. So, once you have this 0 to infinity, because there is a boundary in your domain, so at which you have to give the initial conditions. At 0, you should provide the initial conditions. So, y at 0 and y dash at 0 up to y n minus 1th derivatives at 0, you have to provide the conditions. So, once you give those conditions, you apply this cosine transform or sine transform. So, right now you have this minus infinity infinity. So, these things you will see as and when you do the problems, depending on the domain, how we apply the Fourier sine transform and cosine transform. We will see that when we do the applications when we do the problems. So, right now I will consider this general problem, general just equation. So, how do we solve this? We apply Fourier transform. So, what you get is a n d n y by dx power n, for which all function of psi, and you have similarly a n minus 1 d, these are constants. Okay, where a n minus 1 up to a1 a0 are constants. Let us take it as constants. Okay. If it is function of x, still have to worry. So, because it is a product of two functions, so you have to consider such a transform. So, if it is a constants, as of now it is easy. So, you consider like this dn minus 1th derivative. For this, if you take the Fourier transform and so on. So, you end up getting a1 dy by dx, for which you take the Fourier transform, and you have a naught y transform. Y is a function of x, a naught is constant. So, what you get is f cap of xi. Xi belongs to full real line. So, this is what you have if you apply. And now, because a n is it's a linear transformation is linear. So, a n is because it is a constant, it comes out, and its nth derivative is I xi power n into, if you repeatedly do the integration by parts, and in the definition of the Fourier transform, you send all these n derivatives onto exponential function, and what you get is Fourier transform of y. This is what is the Fourier transform of nth derivatives. So, like this you go on. So, you have a n minus 1 constant comes out, I xi power n minus 1 into y cap of xi. So, you see that every time you are ending up only y cap, Fourier transform of y. So, and you get a1 I xi into y1 cap y cap of xi plus a naught y cap of xi, which is equal to f cap of xi. This is what you get. So, what we need is, so y cap is y cap of xi is common, y cap of xi, and what is this one? This is actually equal to, if you, because the way you have defined Ly is this. So, what you end up is, so L of so this is a polynomial, right. So, you cannot write in terms of L, though L is some operator. So, let me write as a polynomial. So, a n I xi power n up to a1 into I xi plus a naught. This is the polynomial in xi, which is equal to f cap of xi. So, if you call this some q xi or whatever, so if you, let us call this some p n of xi nth degree. So, you have y cap of xi is actually f cap of xi divided by p n of xi. So, what we need? We have now this one, as xi belongs to full R. Now, if you can take the inverse transform here, so what you get, if you take the inverse transform for y, you get your yx. That is exactly the solution of this equation. So, such a solution is actually inverse transform of this, that is actually minus infinity infinity 1 by root 2 pi f cap of xi by p n of xi e power I xi x d xi. So, this is exactly your solution. If you can evaluate this nicely, that is what you will get as a solution. So, this is the general procedure to find the solution of this equation. Okay. So, this is one. So, if you actually, if you know the differential equation theory, because if it is the nth order differential equation, the solution you might have seen C1 times y1 and C2 times y2 and Cn times yn, which is a homogeneous solution, plus some particular solution yp of x. What you get here by this solution, this is called particular solution. When you put y equal to f is 0, you are getting y equal to 0. Okay. So, if you take f equal to 0, so your solution what you got by Fourier transform, you put f cap, if f is 0, f cap is 0. So, that makes it y equal to 0. If f equal to 0, you get y of x equal to 0. So, from this method, okay, from this is what you get. So, that means you are not actually calculating homogeneous solution, but this particular solution, okay, that is actually the general solution of this equation. Okay. So, if you so that is how we solve, we get only a particular solution here. So, just if you do like this, you get a particular solution, because there is no boundary involved here. Okay. So, if you are given a full solution, full domain, if you apply the Fourier transform, what you get is only particular solution. Okay. So, let us do some example. We start with an example here where we use full Fourier transform. So, example what we considered here is d square y by. So, solve this problem d square y by dx square plus 3 dy by dx plus 2 y equal to e power minus x. So, what is surprising here is if I take x full real numbers, e power minus x when x is negative, this is unbounded thing, so that you cannot take the Fourier transform. So, that is not absolutely integrable function from minus 0 to minus infinity or minus infinity to 0. So, so what is given, the domain is actually positive. So, in this you have to solve, and the boundary initial conditions are, so this is y of x, the domain is this 0 to infinity, this is the domain, and on which you have initially, because it is a second order equation, you have got to give two initial conditions. So, those are y dash of 0 and y of 0, they are given as 0. Okay. So, and what is the other boundary? This is infinity. You can assume that y and y dash they are going to 0 as x goes to infinity. So, this is because you have the infinity. Okay. Once you have such a thing, so this is your problem. So, if you view this as a initial value problem, and you can consider this as initial value problem, if you choose only this one, and if you choose one of the values, one of these conditions here, and then if you use this one, that is a boundary value problem. So, let us solve only initial value problem as of now. So, let us take this initial value problem, let us solve, and then solution goes like this. So, how do we solve this? What is given is on x positive side, you have this y of x is defined, and so how are we going to solve this? So, but we have, if we want to apply the full Fourier transform, you need from x belongs to minus infinity to infinity. So, I extend this y of x from 0 to infinity to minus infinity to infinity. So, how do I do this? So, as though y is actually y is if you restrict to 0 to infinity, it is this solution, otherwise it is as though it is extended from minus infinity to infinity. Then what is the equation now? So, equation now is d square y by dx square and dy by dx plus 2 y, where y of x is here, and then this is equal to, now I have e power minus x when x is positive, that is x is positive, and what I do is I take 0 when x is negative, less than or equal to 0. This is actually same as saying e power minus x times h of x. So, this is how if I take that extension, because the negative side it is already y of 0, so y of 0 is actually 0 and y dash of 0 is equal to 0. So, suppose these two are conditions are given at this point. Okay. Now, if you take x less than 0, less than side, negative side, what happens? Because these two initial conditions, your equation is y double dash plus 3y dash plus 2y equal to 0. So, you have a homogeneous equation with the homogeneous boundary conditions, which are homogeneous initial conditions that are given. The solution is actually completely 0 for every x in minus infinity to 0. So, if you choose these conditions, so and your equation, because your equation and the negative side is 0, you have completely negative side for all x. Your solution yx is already there. It's the way you choose your initial conditions, that makes it y of x is actually 0, y of x is 0 for every x less than or equal to 0. That is clear. Okay. The solution is actually, solution is this, because of the initial conditions. Now, only thing you have to worry about x positive side, that is what when you choose x positive, it is e power minus x. So as such, So, this is ad hoc way. So, you look at only negative side, and at x equal to 0 these conditions are satisfied, y x is actually completely 0. So, these conditions are already utilized, the negative side. So, that way now you consider what happens for x belongs to minus infinity infinity. If you look at it, this is e power minus x times h of x. So, whenever you have these 0 boundary conditions, you can extend it this way with the Heaviside function, so that your solution negative side is always 0. Okay. And then so the initial conditions are anyway satisfied. Okay. These conditions are already utilized, that sense. Okay. Now, if you apply for this full equation, if you apply Fourier transform, and so what is that apply? If you apply d square Fourier transform of y dash, if I write d square y by dx square as y double dash Fourier transform of psi plus 3 times dy by dx, that is y dash of xi cap of xi plus 2 times y cap of xi equal to you have e power minus x h of x this cap of psi, that is what you have to choose. So, if you calculate this one, so what is this Fourier transform of 1 by root 2 pi. So, right hand side what we need is 1 by root 2 pi. So, its Fourier transform is 1 by root 2 pi e power minus x h of x. H of x is negative side is 0. So, 0 to infinity is 1, and you have e power minus I xi x dx. So, what you get is 1 over 1 plus I xi, if you, and 1 by root 2 pi is a constant, and so e power minus x times 1 plus I xi. Okay. So, minus of course minus is there. So, if you apply 0 to infinity, this is actually equal to 1 by root 2 pi 1 over 1 plus I xi. So, the inverse transform of this is actually e power minus s x h of x. If you are given like this, you can easily see the inverse transform as e power minus x h x. So, here because it is a derivative, if you take the Fourier transform, what it comes out is I xi square for 2 derivatives into y cap of xi. It is the property of Fourier transform, and here e power 3 times I xi times y cap of xi, and here 2 y cap of xi. So, y cap of xi is common here all places. So, you have this equal to, here you can write 1 by root 2 pi 1 by 1 plus I xi. So, what is your y cap of xi is 1 by root 2 pi 1 by 1 plus I xi into 1 divided by, I have I xi square is like, if I put I xi as x square plus 3x plus 2. So, you have x plus 1 into x plus 2, you can write this. So, if you write like that, you have I xi plus 1 I xi plus 2. So, this if you write it as a partial fractions, so let me write this as a partial fractions. If you write minus 1 by 1 plus I xi plus 1 by 1 plus I xi whole square plus 1 by 1 plus rather 2 plus I xi. So, this is what is after partial fractions. So, now you can invert it, y cap, if you invert your y cap, take the inverse Fourier transform, that will become y x, which is equal to by the integral Fourier integral theorem. And then if you do here, so for this if you apply Fourier integral theorem, what you see is you can easily see for this inverse is e power minus x h x. So, minus of e power minus x h x, and here plus, and this will be, so if you have a square what you do is you try to get this Fourier transform of e power minus x times h x, for which you multiply x for this full transform. If you multiply x, any x power k, and if I choose this as a function f x, this is actually equal to, if you use take it as a property, you can prove it. This is you can actually show that this is equal to what you get is 1 by root 2 pi 1 by 1 plus I xi whole power k plus 1 times f cap of xi. No, something else you will get. So, you get no, not this way. So, what you get is f cap of xi power k plus 1 you get, that is what you will get. Okay. So, can we see this one? If you do simply for k equal to 1 f x cap of xi, if you do this 1 by root 2 pi minus infinity to infinity x f x e power minus I xi x dx. So, I try to take this as so integral value of this maybe. So, you can just if I substitute this is easier. So, if you take e power minus x h of x, if you take this is actually equal to 1 over 1 plus I xi power k plus 1. So, this is at least this you can think of. So, for every k belongs to the natural numbers. Okay. So, you choose this if you do f as this e power minus x into h of x, then what you get, if you replace this is going to be e power minus x and this is going to be 0. So, once you have this is equal to 1 over root 2 pi and you have a e power minus x. So, what you get is minus e power minus x 1 plus I xi divided by 1 plus I xi, that is the integration, and you multiply and into x you substitute the limits. Because of x this is 0 and you have a minus plus now 1 by root 2 pi minus, so 0 to infinity you have e power minus x times 1 plus I xi by 1 plus I xi into derivative of x is 1. So, you have dx. So, this is actually equal to 1 by root 2 pi and you see again. So, 1 by 1 plus I xi comes out and this integral as you can see here. So, there is going to be 1 more 1 by 1 plus I xi. So, there is a square. So, you can easily see that this is the just by inspection you can see that if it is something if you know already the square of this kind of you instead of replacing this with some function f, if you know how to evaluate, so that it is Fourier transform and then what you end up is power of Fourier transform of such functions power k plus 1. So, this is what you see. So, you can easily see here that this is going to be e power minus x h of x times x. So, you have x times this and here this one e power minus 2 x h of x. This is x belongs to minus infinity to infinity. Okay. So, what happens when y x equal to 0 clearly. So, the solution is actually you can easily see here x is less than or equal to 0. So, once you have this one y of 0 is automatically satisfied, y dash of 0. So, that is the reason if you are given these 0 boundary conditions, 0 initial conditions, you always extend your right hand side function with Heaviside function for which you have the Fourier transform, you know how to evaluate. And what happens at y x positive, y x is equal to minus e power minus x plus x e power minus x plus e power minus 2 x for x positive. So, this is your solution and this is the negative side of that. And now, even if you use this one, because let us see whether if it is continuous or not, y of 0 is actually equal to. So, as you see this is the differential equation. So, what you are looking for is the solution y that has derivatives. Okay. Right hand side is kind of forcing both the x positive and x negative side. One side is anyway these conditions are satisfied, the other side also you can easily see conditions that if you put y 0, this is going to be minus 1 plus 1, so which is 0, and y dash of x is e power minus x plus minus x e power minus x plus e power minus x minus 2 e power minus 2 x. So, if you put x equal to 0, y dash of 0 is 1 plus 1 minus 2, this is also 0. So, these conditions are automatically satisfied because y is a continuous function. The solution that you calculated is a continuous function. Okay. So, this is what you are looking for is the solution that automatically satisfies these boundary conditions. So, and this is not the only way to prove to solve this equation. You can also solve this equation because the domain is the only positive side. You can apply cosine transform or sine transform directly, and you can there you do not have to worry directly. These coefficients will come into the picture. So, those things whatever may be the value, when it is non-zero you can use cosine and sine transforms. Only when these both the conditions are 0 you can use the direct Fourier transform by extending with the Heaviside function. Okay, we will see some more example in this direction. Maybe in the later on we will try to solve these problems with cosine and sine transform. So, let us do some more problems. For example, let me use one more example. One more example is solve y double dash minus 4y dash plus 4y equal to x into e power minus x, x positive. So, and y of 0 is 0, which is y dash of 0. If you are given like this, so the solution as usual you can proceed because it is a 0 boundary condition, you can extend this to a full real line. Okay. So, with Heaviside function. So, you extend y of x, x belongs to minus infinity to infinity. Okay. So, you have a solution equation is now 4y dash plus 4y equal to x e power minus x into hx. Now, h belongs to minus infinity to infinity. Now, your conditions are automatically satisfied. As you see, negative side is always at that point is 0, it is a homogeneous equation, the negative side. The solution is actually, you know that homogeneous equation with 0 initial conditions is always 0, completely identically 0, y of x equal to 0 for x negative. So, these conditions are automatically satisfied for this equation because at x equal to 0 it is completely 0. So, your x equal to 0 also is given 0. So, let us see what happens. So, let us solve, we are not solving by splitting it like that, and we will try to solve this together as though this is one function. Okay. We do not split the domains and do this. Even if you split, you can see that this one, you clearly see that these conditions are automatically satisfied on negative side at x equal to 0. So, now look at as usual apply the full Fourier transform. You see that I is I whole square y cap of xi minus 4 I xi times y cap of xi plus 4 times y cap of xi, and here is the Fourier transform of this. We have seen earlier that this is 1 over 1 plus I xi whole square. Okay. So, if you apply this one x square, so if you look at this one, this is y cap of xi is equal to 1 over this is when you get this you see that 1 by root 2 pi. So, you have 1 by root 2 pi missing, and what you get is 1 by root 2 pi 1 plus I xi square, and here 1 over if you divide. So, I xi square minus 4 I xi plus 4, that is like x square minus 4x plus 4, that is going to be I xi minus 2 whole square, right, I xi minus 2 whole square, that is I xi square minus 4 I xi plus 4. So, that is what is the left hand side. So, this is what you have. Now, if you use the partial fractions 1 by root 2 pi. If you use the partial fractions, I write directly here. So what I do is first 1 by 1 plus I is I, you have something divided by 1 by 1 plus I is I plus something, some number into 1 by 1 plus I is I whole square plus something, this is here 2 minus or I is I minus 2, I is I minus 2 plus what is divided by I is I minus 2 whole square. So, if you make this as some numbers A, B, C, D, and you can multiply, and then you can see, you can equate the coefficients of, by partial fraction method you can find, I will write directly, it is going to be 2 by 27, you can verify this, and it is going to be 1 by 9, and this is going to be minus 2 by 27, and this is 1 by 9. Okay. So, this is exactly our y cap of xi, and if you invert this, the first term will give me 2 by 27 e power minus x h of x and plus 1 by 9 e power minus x into x h of x, and here is going to be minus 2 by 27, and this is going to be e power minus this e power 2x into h of x because of minus 2. Okay. If you calculate this Fourier transform, you will see that it is going to be this one, and this one will be plus 1 by 9 x e power 2x h x, and where is this valid? From minus infinity to infinity. So, if you look at if you look at negative side, it is completely 0, that is what we get, and for positive side, that is what we want, which is equal to 2 by 27 e power minus x plus 1 by 9 x e power minus x minus 2 by 27 e power 2x plus 1 by 9 x e power 2x. This is for x positive side, that is what we want. Now, if you verify this y of 0, 2 by 7 and minus 2 by 7, that is 0 clearly. Y dash of x, if you calculate 2 by 27 e power minus x with minus sign, and here plus 1 by 9 e power minus x minus 1 by 9 x e power minus x minus 2 by 27 times 2 e power 2x plus 1 by 9 e power 2x plus 2 by 9 x e power 2x. Now, this if you put x equal to 0, okay. So, what you get is a y dash of 0 minus 2 by 27, and you have plus 1 by 9, and here minus 4 by 27, and you have 1 by 9, and this is actually same as 0 again. So, minus 6 by 27, there is 2 by 9, already you have 1 by 9, 1 by 9, that is 2 by 9, this is 0. So, both the conditions are satisfied, this is what we verified. Okay. So, the actual solution what we are looking for, even if you solve by other methods, you should get, you are getting this, this is your solution of the initial value problem that is given as here. If we solve also by a cosine transform or sine transform, because it is it's given in the semi infinite domain. So, you can solve even those by those methods, that we will see later. Okay. So, let us solve one more example, but this is not that straightforward. This is let us do this. Solve y double dash minus 4y dash plus 5y equal to 1 now. So, this is x positive. So, the solution we know already what is its solution, and so the conditions are also same, given as 0 y and its derivatives at x equal to 0. Okay. So, if you do this, what is if you follow the same way, the moment you see these initial conditions, you can extend this to x belongs to minus infinity infinity to get the equation y double dash minus 4 y dash plus 5 y equal to h x. Now, this is x belongs to minus infinity infinity. Again, these conditions are automatically satisfied at the negative side. This is identically 0 solution. So, and what happens now? So, what happens if you apply the Fourier transform like earlier, I is I square minus 4 I is I plus 5 times y cap of xi, that is the left hand side. What is the Fourier transform of h x? That is h cap of xi, that is h cap of xi we have seen earlier that this is not, this is actually what you get is with our definition root pi by 2 delta function of xi plus 1 by root 2 pi 1 over I omega y xi. So, this is your Fourier transform. So, if I write this here root pi by 2 delta function of xi and then plus 1 over root 2 pi 1 over I xi. So, what I do, what I get is y xi is, so y xi is now root pi by 2 times delta xi divided by, so what is this one, x square minus 4 x plus 5, this I can write like x minus 2. So, what is this one? So, if you get the roots of this equation, you will see that roots of the equations are x equal to 4 plus or minus square root of 16 minus 20 divided by 2, where is going to be 2 plus or minus I 2. So, right, 2 plus or minus 2 divided by 2. So, that is going to be this. These are the roots. So, because of those are the roots, so you can rewrite this as I is I minus 2 minus I for 2 plus I, and other one is I is I minus 2 plus I. This is one term, other term if you rewrite like this 1 by I is I 1 over the same this division the left hand side I is I minus 2 minus I and I is I minus 2 plus I. So, this is what you have. So, if you try to take the Fourier transform, so before you take the Fourier transform, so what happens here? So, this is going to be root pi by 2 delta xi, this you write as it is I is I minus 2 minus I is I minus 2 plus I. This one again you apply partial fractions and rewrite, after writing partial fraction directly write as 1 by 5 divided by I is I plus 1 over, if I write minus 2 plus 4 I divided by I is I minus 2 minus I, and here one more thing is 1 over minus 2 minus 4 I divided by I is I minus 2 plus I. You can verify that this is same as this second term here. So, once you write like this, now you can take the inverse transform. What is the inverse transform of this? The inverse transform of this one, inverse transform of this, inverse transform of each of these 4 terms. So, first one is you do not know exactly what is the inverse of this, because it involves the delta function inverse, you use the inverse transform definition, that is 2 pi minus infinity infinity root pi by 2 delta function divided by I is I minus 2 minus I and then I is I minus 2 plus I times e power I is I x dz. And this is you can easily, because of the delta function, simply substitute z equal to xi equal to 0, that will do, that will give the value of this integral. Other integral is you can 1 over 5 comes out, and the remaining 1 by root 2 pi I xi is e power minus okay, this is this, if you again if you use this e power I xi. So, this is what, for this if you want inverse transform of this minus this. What is inverse transform of this? This is hx minus this we have seen already, this is inverse transform of this is half, because Fourier transform of half is actually you get this value. So, the inverse transform is half. So, hx minus half, okay. And then here 1 over minus 2 plus 4 I times, and this is going to be, so what do you get? Again, like earlier, you have e power because of this minus, and you get a plus sign. So, you have a 2 plus I times x times hx, okay. And then one more term is you have this partial fraction, that coefficient minus 2 plus 4 I. So, minus minus comes out, I put it here, and then what you have here is e power 2 minus I x times h of x. This is for x belongs to full real line, that is minus infinity infinity. So, this is exactly your solution. So, what happens to the first integral? Because of this delta function, root pi goes, and you have root 2 both the place in the denominator. So, you have 1 by 2, and when you put xi equal to 0, that is simply 1 by 2 minus I minus 2 minus I times minus 2 plus I. So, it is going to be 4 minus 2 whole square, 4 minus I square. So, going to be 5. So, together 1 by 5, that is into 10, that is going to be 1 by 5 into 1 by 2 is 1 by 10. So, the first integral is this, and the second integral, and this 1 by 4 and minus 1 by half, that is going to be 0. So, that is gone, and what you have is 1 by 5 h of x plus, and this is what you have. So, you have e power 2 plus I x by minus 2 plus 4 I hx 1 divided by 2 plus 4 I e power 2 minus I x h of x. This is x belongs to minus infinity infinity. So, this gives me a solution as 1 by 5 for x negative. X positive side is anyway 0. So, because you have a 0 boundary 0 initial conditions with homogeneous equation, you have a yx is 0, completely identically 0 solution in the negative side. A positive side 1 by 5 plus e power 2 x is anyway common, and divided by minus 2 plus so you maybe have to see this one, e power I x divided by minus 2 plus 4 I, then minus e power minus I x divided by 2 plus 4 I. Okay. So, this is for x positive side. So, we will simplify this 1 by 5 plus e power 2 x. So, I multiply minus 2 minus 4 I multiply and divide, so that you have e power I x times minus 2 minus 4 I, and the denominator you have 4 plus 16, that is 20, and here again I multiply 2 minus 4 I, and the denominator if you divide the same and you multiply with 2 plus 4 I, that is going to be again 20, 4 plus 16 20. So, as you see 1 by 5 plus e power 2 x is common, and you can simplify this, that 10 comes down, and what you get is e power I x minus 1 minus 2 I, here e power minus I x 1 minus 2 I. So, if you take it out, minus comes out, this is going to be plus and this is going to be plus. So, this is going to be 1 by 5 times e power 2 x by 10, and this together is 2 cos x. So, you have 5 cos x, and then here minus e power 2 x by 10, and you have e power I x minus e power I x. So, you have 2 I times e power I x minus e power I x is you have again 2 I sin x. So, that makes it e power 2 x by 5 cos x, and here, so this 2 is 5. So, you have this is going to be plus, I square is minus 1. So, that makes it plus. You have e power 2 x sin x 2 e power 2 x divided by 5. So, this is what you have as your solution. So, your y x is this solution. Okay. So, as you can see, when you substitute y at 0, cos 0 is 1. So, you have 1 by 5 minus 1 by 5, that is 0. This term is 0. So, it is clearly y 0 is 0, and if you calculate y dash of x, which is this is if you differentiate this is 0, and here you have sin x e power 2 x by 5, and here a minus 2 e power 2 x cos x by 5, and again if you do differentiate this term, so 2 by 5 cos x e power 2 x, and this gets cancelled anyway. So, and then if you differentiate this part, you have 4 by 5 e power 2 x sin x. Now, if you substitute y dash of 0 here, this term is 0 because of sin x, and because of sin x, that is 0. So, you have y dash of y at 0 is 0 and y dash of 0 is also 0. So, these two are verified. Okay. So, with this we can easily see that this even though one is not a absolutely integrable function in this example, you can actually extend this as with Heaviside function. Heaviside function has a Fourier transform in terms of a delta function, because these see we are minimum having a we are doing the Fourier transform of very few generalized functions. Usual functions anyway we know how to find Fourier transform, but generalized functions also, that too only 1 or 2 which comes in the application, for example Heaviside function or the delta function itself. Only these two you see how to find the Fourier transform we have already seen. So, we make use of them to evaluate to solve this simple ordinary differential equation, okay, with the initial data. When it is zero boundary, zero initial conditions, you can solve that, you are able to solve just by using the Fourier transform, full Fourier transform. So, you do not have to do this way. So, you can also do all these problems using Fourier cosine transform or Fourier sine transform, because the domain is semi infinite, that is between 0 to infinity. So, these things we will see maybe in the next video. Thank you very much.